So, hello and welcome everyone. Welcome to week 10 of interactive live sessions for the course on fundamentals of convective heat transfer. The course is being offered by NPTEL and is being instructed by Professor Amaresh Dalal from IIT Guwahati. Uh, I am Debjit, I am a TA of this course and we shall be solving some tutorial problems together. So, like every week, let us begin. So, we will begin with question number 1 of today's session, which is a match the following kind of question where there are two columns. The first column being option A equilibrium problems and option B marching problems. You'll have to match that with the type of PDEs which usually appear uh, for these kinds of problems. So option 1 parabolic PDE, option 2 hyperbolic PDE, and option 3 elliptic PDE. And
Answer C.
option C. So there are four options. Option A says A1 and B2. Option B says A2 and B3. Option C says A3 and B both 1 and 2. And option D says A both 1 and 2 and B only 3. So you're saying that the correct answer is option C. Is that right?
Yes.
Okay. So if we have a look at the solution. So the solution is incorrect. It's A3 and B1 and 2. So in equilibrium problems, these two in sorry, in equilibrium problems, elliptic PDEs show up, and in marching problems, it's either parabolic PDEs or hyperbolic PDEs. So among the examples which were cited in the lecture, uh, the heat diffusion problem, simple steady heat diffusion, the double gradient of temperature being equal to zero, or the Laplacian of temperature equal to zero. This kind of a PDE is elliptic, as well as this is an equilibrium type of problem. It reaches a stable equilibrium and stays there. Uh, on the contrary, uh, let's say some initial value problems which develop in time, as well as wave problems. Those are hyperbolic PDs, and those are the kinds of marching problems. Now, within marching problems, there can be two types. One is time marching, and the other is space marching. So, in time marching, what is that? There is a fixed domain. The space is fixed. Let's say it goes from say x equal to 0 to L, but this goes on marching in time. So t goes from 0 to infinity, and uh, we are concerned only about the part that which matters to us. That's what we try to solve for. Uh, on the contrary, let's say the development of a boundary layer, that kind of a problem is not marching in time, but that's marching in space. Because x can go from 0 to infinity, the boundary layer would, in theory, keep growing uh, along with the distance x. So this is a space marching problem, and this is a time marching problem. So these are some very few simple examples which usually show up in convective heat transfer.
Yes.
Now we will quickly move on to question 2. Question 2 says select some numerical schemes which are usually used for solving convective heat transfer problems. Option A, finite difference method. Option B, finite element method. Option C, finite volume method. Or is it option D, all of the above?
First, finite difference. Actually, all three can be applicable, but mostly finite difference.
The correct answer is all of the above. Not
Hmm.
only finite difference, finite volume is also very extensively used for
CFD. CFD.
CFD.
CFD.
CFD is a broad branch. Now, within that, finite volume and finite difference are the most popular ones. Finite element method is also used. It has some very specific uses. Uh, now, usually, when there is fluid flow, finite volume method is preferred above finite difference method as well. It has some computational advantages, especially when the geometry is not a regular one. Then finite volume method has its uh, advantages over finite difference method. But all these three methods are actually can be used for solving convective heat transfer and fluid flow problems. Okay, so moving on, we will move on to question 3, which is that order of accuracy of forward difference discretization scheme is what? Is it option A 1, is it option B 2, or is it option C insufficient information? Like, what it means is the question does not carry sufficient information to land on a correct answer.
Utilization method. Is it one, sir?
No, it's actually insufficient information because see, if we use only 2 points, let's say, sorry, if we use only 2 points, let's say I and I plus one, and we use forward difference to, let's say like ti plus dou t dou x. If we write that as dou ti plus 1 minus dou ti divided by delta x, this is first order accurate.
Yes.
But we can use more points, let's say I plus 2, I plus 3, and so on. Forget about I plus 3. Let's say if we take 3 points and we say that dou t dou x is equal to some alpha ti plus beta ti plus 1 plus gamma I plus 2, and we then uh, use Taylor series expansion on all these and try to solve for these alpha, beta, and gamma, then we will get pure numbers. Like in this case, these are 1 by delta x and minus 1 by delta x, which are coefficients of ti and ti plus 1. Similarly, we will get some coefficients for alpha, beta, and gamma. But in that case, the order of accuracy will be second order. Similarly, we can use more points to increase this order of accuracy.
Okay. So it depends on how many points we are
It
taking.
depends on how many points we are taking.
Hmm.
Now we will move on to question 4. So question 4 says explicit schemes are. So we have learnt about different schemes, explicit schemes and implicit schemes. Now, what is the stability criterion of explicit schemes? Are they option A unconditionally stable, option B unconditionally unstable, or is it option C conditionally stable?
Probably conditionally stable because
Conditionally.
implicit schemes are unconditionally stable.
Hmm. Correct. So we have seen that in explicit schemes, our delta t, the time step that we take, or the minimum time in which we discretize, this has to be less than some critical uh, delta tc. So this is determined by the spatial discretization. So if we take finer and finer grids, this delta t will also have to go small in order to make sure that the scheme is stable. Otherwise, what happens is the information transfer happens at a slower rate than the sorry, was it slower or is it higher? It happens at a slower rate than the actual transfer of the physical quantities like velocities or temperatures, and that leads to uh, giving incorrect solutions. That's why the numerical scheme becomes unstable, and it gives tending to infinity or tending to negative infinity kind of solutions.
It is
So
like divergence.
divergence, correctly. So the error, instead of decreasing with more iterations, the error blows up, and the calculated values, they actually uh, tend towards infinity and negative infinity. And That's why explicit schemes. This is actually a disadvantage of explicit schemes. So our time step that we take is actually limited by the grid as well as the other discretization schemes which we use. Implicit schemes, on the other hand, depending on which scheme we use, are some of them are unconditionally stable. Like we can take any delta t that we want to. Uh, the solution method would still be stable. Now, there are in fact some implicit schemes which are unconditionally unstable as well. These are some bizarre examples which are not, directly applicable, but they some mathematical insight uh, can be drawn from those. Okay.
Okay.
Okay. So moving on, we will move on to the question 5 of today's session. So, what are the different ways in which we can solve for implicit schemes? Is it option A, Kramer's rule; option B, Gauss elimination; option C, Jacobi method; option C, Gauss-Seidel method; or is it option E, all of these?
Please sit. Actually, out of that, Gauss-Seidel is iterative method. Jacobi is also iterative, but Kramer's and Gauss elimination are not iterative. So Jacobi and Gauss-Seidel.
The correct answer is all of these. You were right in saying that these are iterative schemes, and these are direct methods, but all of them can be used for solving implicit schemes. See, basically, what happens in explicit schemes, we simply know the uh, you know we simply know the value of, let's say, some quantity that we're trying to solve for, let's say temperature in this case, in terms of other quantities, other known quantities which are at, say, time level n. uh, the problem with implicit schemes is that instead of getting this directly, we will get some, you know some function of, uh, okay, not like this. We will get some linear combination like this of the values at n plus 1, multiple values at n plus 1. So we have uh, multiple unknowns as well arising out of each equation, something sort of like this equal to some known quantities clubbing up together to give some value. Now, the problem with this is that we cannot solve this directly. So, what we'll get instead is a series of similar equations, and we can write them, we can boil them down to some matrix operations. Let's say some containing Tn plus 1, and this containing all the C's or the constants C1, C2, C3, and so on, and equal to another column matrix of the values that we know. Let's say we let's say I'm calling this B. So this is a constant column vector that we know. This is also a constant column vector that we know, and this is what we're trying to solve for. So okay, this does not have to be a column. This could be a matrix as well. Let me write this correctly. So this would be a vector, and this would be a matrix, and this would be equal to another vector as well. Now, in order to solve for this vector, we can either use direct scheme. Kramer's rule would be directly multiplying the inverse of this C matrix on the right hand side, and we can get this directly. Gauss elimination also follows a similar method, but in that case, you know, diagonalization has to be done. But the other ones, the iterative ones, there some guess value of this temperatures are taken, and then some numerical scheme is there. They're different for Jacobi method and Gauss-Seidel method for let's say other schemes like successive over relaxation method SOR. There are different mathematical ways of doing it, but uh, the overall idea is we take some guess value, we iterate, um, we iteratively keep calculating those values and keep improving them. And once they are uh, you know once it
Error limit.
converges, the error goes down below some level, we stop iterating and we take that solution to be the correct solution. Now the benefit of iterative solutions is that they are faster as compared to direct methods. Direct methods would give you the accurate answer, but it's computationally heavier. Some calculating the inverse of big matrices like which usually show up in CFD solutions is actually a heavy task for even very high-end good computers. So for that reason, iterative methods are preferred.
Sir, if the question is like this, explicit schemes are solved by,
Hmm.
then
Sorry, I wasn't able to understand. Can you?
solution methods of explicit methods.
Yeah.
Yes.
Okay. The language is brief. Is that what you're saying?
No, no. Actually, if the question is instead of explicit schemes, it is explicit,
Hmm.
implicit ki jagah. So which
Oh, okay.
methods we are using?
No, no. Then all this mathematical circus is not required for explicit schemes. We are directly getting this. No, we will simply iterate this over I, j, k, and
Hmm.
get the values for each t.
Okay.
See, we have a formula that t equal to something, some function of something. Now we will simply, if you're writing a code, we will iterate this over, let's say, I to what was that used? I in the lectures, what was used? I equal to 1 to I RE, and for j equal to 1 to JRE. These are the last points which are being taken.
Mm-hmm.
We will simply iterate this over each point, and for each point we will get the value of t. This is, sorry, let me write this correctly. This is t of I comma j. This function is known, all the values inside they are also known. So each value of t at each I and j can be found out like this. Since we know the formula directly,
Yes.
explicitly. That's why it's called explicit scheme.
Means function directly known.
That is directly known. But implicit scheme, then there is no one t that we know. There are multiple three or four t's which come in one, linear combination, and this equal to something that we know. But there are these three or four or more unknowns in one equation. Since we
Mm-hmm.
can't solve them directly, that's why all this mathematical, circus is required. We have to create matrices, huge matrices, and then try to solve for the unknown values. Okay,
Yes.
so moving on. So MAC algorithm. Now the steps of MAC algorithm are given in the left column, and in the right column, uh, the order of them are given. So you have to, go through those steps and figure out the correct order in which they have to be implemented so that MAC algorithm is correctly followed. So the steps are, let's say, step A says initialize U, V, W, P, and T, all the velocities, pressure, and temperature.
No, it has to
Uh,
start with initialize only. So
okay,
init.
so
Yeah.
and that doesn't help you because all the
It is there in
options also
option.
start with A.
Mm.
Now, step B says check for convergence, repeat if necessary. Step C says predict provisional velocities. Step D says solve for scalars. Step E says update velocities. And step F says find pressure correction. Now, one
Mm.
important hint is option B, check for convergence and repeat if necessary. So that is usually the last step. Like everything
Last.
has been done, check for convergence and repeat if necessary. If not necessary, proceed with it as solution.
Hmm.
So option B would be the last one. So A at front and B at end. So option A is incorrect. So it has to be within B, C, and D.
Hmm.
Now,
Yep.
within B, C, and D, the difference is within the second and
B.
the third
B,
step,
sir.
whether
B.
it's, sorry,
B. B. B.
option B. So it's A, C, F, E, D, B. Let's have a look at the correct answer. And it's indeed the correct answer. So option A, step A, initialize U, V, W, P, and T. That is the starting step. Then step C, that is predict provisional velocity. So we saw that using uh, the MAC formulation, we can use the values at the current time step n and calculate some provisional velocities, which are usually shown using u tilde, v tilde, and so on. Tilde values, these are provisional velocities. So we calculate them uh, in terms of the known quantities at the nth time level. So this is the first step. This is the second step. Then what do we do? Then we calculate the pressure corrections in terms of the provisional velocities and other known values. Okay, so calculating the pressure correction is the next step. So F would be step 3. Then using, after knowing the pressure corrections, and another important assumption also we plug in here, which is we take that the pressure corrections in the neighboring values in the neighboring cells are 0, and we try to find out the pressure correction in the given cell only. So in that way we can find out the pressure corrections in all the cells that we are concerned about. So finding the pressure correction is step 3. Then using that we will update the velocities. So that is step 4. So now uh, u and v n plus 1, that is at the next time step, that is found out in terms of pressure correction u tilde, v tilde, un, vn, and so on. So this step would be the fourth step, and after that, once we have the velocity solution, we plug those values in the energy equation for solving for t, that is step 5. If there are other scalars, let's say like in combustion or chemical reactions, while we're modeling those, the mass fractions are also an important uh, you know parameter to be calculated. So those are also scalars, and those scalars can also be solved in this step, that is step 5. After that, we will go to the last step where we will check for convergence, and if our solution has converged, we will stop at that point and uh, walk home happy with our solution. Other than that, if it's not, then we will keep on iterating this until we are happy with it.
Yes.
So this is the correct order: A, C, F, E, and D, B for implementing MAC algorithm. Another name is also used here, that is predictor corrector method. So we predict this provisional velocities and then correct the pressure using this. Okay. So moving on, we will move on to the problems of using staggered grid. Which are those? Is it option A, checkerboard pattern appearing? Is it option B, pressure velocity decoupling? Is it option C, both A and B? Or is it D, none of the above?
Checkerboard pattern.
Let's have a look at the correct solution. It's actually both A and B. Uh, these are actually not very different things. Checkerboard pattern appears due to pressure velocity decoupling only, uh, or the you know, let's take an example and see. So let's say this is our computational grid, and we take values. We take a collocated grid. Okay, sorry. I'm wrong over here. The question should have been problems of using collocated.
That's why actually staggered grid is having strong coupling between
Yeah,
pressure and velocity.
staggered grid is the solution to this. Sorry,
Mm.
there is a typo. So, what are the problems of using collocated grid? That is checkerboard pattern and velocity pressure decoupling. So, what happens is if we take a collocated grid like this, the pressures are here and the velocities are also in this step, in this point only. Now, let's say this is I plus 1. Okay, sorry. Let's say this is I minus 1, this is I, and this is I plus 1. So, uh, let's say in the momentum balance equation. So, and if we take a central difference, then we will consider the value. Okay, sorry. Then we will consider the value at this point and this point to find out the the pressure values at this point and this point to find out the velocity at this point. Now, if there is a imposed checkerboard pattern, which is something like pressure being 100 here, 0 here, 100 here, 0 here. So if you're trying to find out the pressure difference between this point and this point, that del P would be equal to 0 because these are the same. But uh, and as a result there will be no velocity here, but we can see that the pressure actually decreases from here and decreases from here as well. So if we use central difference along with a collocated grid, this checkerboard pattern would appear as a uniform pattern to the algorithm and it would remain like this. But that is a problem which is solved by using staggered grids. And this issue of the pressure difference not being communicated to the velocity and the velocity difference not being communicated back to pressure, this is called this pressure velocity decoupling. And this issue leads to this checkerboard patterns probably. So that's why the answer is both A and B. Okay.
Yes.
So moving on, we will move on to question number 8. Question number 8 asks us that what are the different upwind schemes? Is it option A first order upwind, option B second order upwind, option C quick scheme, or is it option D all of these?
All of these.
Correct. So first order upwind we saw that let's say if we have 2 points like this at I minus 1 and I, and U is positive, then while taking, let's say, dou U dou X, we will take dou I minus dou I minus 1. The point upwind from the point being considered. We are considering this at location I. If U was negative, then we would have considered it other way. Okay.
Reverse.
Second order upwind is a similar thing, using more points and getting a more accurate result. Uh, Now the issue with these upwind schemes is that uh, there is a fictitious uh, diffusion which comes into play, or it's called fictitious viscosity. Now, in order to tackle this, quick scheme is used. Quick scheme is also an upwind scheme. The full form of this is quadratic. I forgot it. Quadratic implicit scheme for convective kinetic something like that. Let me check and say. 1 second. Yeah. Full form of quick scheme is quadratic upwind interpolation
For convective kinetics.
for convective kinetics. So this takes care of that fictitious diffusion or fictitious viscosity which appears in first order upwind schemes. So that's all for today. Thank you.